Mama, I need a break. I've been working very hard for my exam.
Break? But in terms of science, the activities that you have been involved in do not involve work at all.
That's not fair. I've been studying for quite some time now.
That's true. But do you know what exactly work means in physics?
Not exactly.
In this lesson, you will learn about work. At the end of this lesson, you will be able to explain the concept of work, state the two conditions that need to be satisfied for work to be done, define work in a scenario where a constant force is acting in the direction of displacement, and define positive and negative work. To understand the concept of work, let's look into some situations. A woman at a mall pushes a trolley and moves the trolley through a certain distance. Jerry tries very hard to push a huge boulder, but the boulder does not move. A man tries very hard to pull a fallen tree trunk tied forward with a rope. However, the tree trunk does not move. A man pulls a hand cart through a distance of 500 meters. In the given situations, all the four characters have applied force. But the result of that force differs. The woman and the handcart puller are able to move the trolley and the handcart across a certain distance. However, Jerry doesn't have much success in moving the boulder, and the man is not able to move the fallen tree. In scientific terms, the woman pushing the trolley and the man pulling the handcart performed some work. However, the man trying to pull the fallen tree and Jerry have not done any work.
Oh, I see. That's why you said I haven't done any work. I haven't actually been involved in moving any objects.
That's right. Work done by force acting on an object is equal to the magnitude of the force multiplied by the distance moved by the object in the direction of the force. That is, displacement of the object. Looking at the definition of work, for any work to be done, first a force has to be applied on the object in order to displace the object from its initial position. The initial position of an object could be the position of rest. Therefore, the two conditions that need to be satisfied to say that work is done are: a net force should act on an object. The object must be displaced in the direction of the net force. Now let's check how clear your understanding is about the concept of work. Consider three cases: a book lying on the table, a horse pulling a cart through a certain distance, a man trying to push a huge rock. Can you tell me in which of these cases work is done?
In the first case, where the book lies on the table, no work is done, as we have not applied any force. This implies that the force applied is zero. Hence, the work done is zero. In the second case, the horse applies force to pull the cart across a certain distance. As there is displacement of the cart in the direction of the force, we can say that work has been done. Finally, in the third case, the man applies force to move the rock, but clearly the force is not enough to move the rock. Since there is no displacement in the rock's position, no work is done. Is that right?
Absolutely. That's very good. So, let us now look at defining work. Work is said to be done when a certain amount of force is applied on an object. This force displaces the object through a certain distance s in the direction of the force. Scenarios involving work may be of two types. The first is where the force is acting in the direction of displacement. The second type, where the force is acting in a direction opposite to that of displacement. That is, one of the identified forces F is acting in a direction opposite to the direction of the displacement S. Thus, the angle between the two directions is 180 degrees. Let the work done be W. The force acting on an object be F. And the displacement of the object be S. The work done is the product of force and displacement. Thus, the work done by the net force acting on an object equals the magnitude of the net force multiplied by the displacement of the object in the direction of the force. The unit of work is the product of the unit of force and the unit of displacement. In the SI system, unit of force is expressed in Newton, and the unit of displacement is expressed in meters. Therefore, the unit of work is Newton meter. In the honor of scientist James Prescott Joule, 1 Newton meter is referred to as Joule, denoted by the letter J. Thus, 1 Joule is defined as the work done when the net force of 1 Newton acts on a body and displaces it in the direction of the force by 1 meter. In the CGS system, the unit of force is dyne, denoted by dyn, and the unit of displacement is centimeter, denoted by cm. Therefore, the CGS unit of work is dyne centimeter. 1 dyne centimeter is referred to as erg. Thus, 1 erg is defined as the work done when a net force of 1 dyne acts on a body and displaces it in the direction of the force by 1 centimeter.
Are joule and erg related then?
Sure they are. Let's determine how exactly they are related. A force of 1 Newton is equal to 10 raised to the power 5 dyne. A displacement of 1 meter is equal to 100 centimeters. Thus, the work of 1 joule is equal to the product of 10 raised to the power 5 dyne and 100 centimeters. This is equal to 10 raised to the power 7 dyne centimeters, as 1 dyne centimeter is equal to 1 erg. We get 1 joule is equal to 10 raised to the power 7 erg.
What about the path followed by an object regarding the calculation of the work done on it? Doesn't that affect the work done in some way?
Not really. Consider an object displaced from the point A to the point B on the application of a constant force F. The object can be displaced from A to B in any of the paths, that is, P1, P2 or P3. But the displacement of the object still remains the same, that is, S, the shortest path from A to B. Work is equal to the product of force and displacement. As you can see, force and displacement are constant regardless of the path the object traverses. Thus, the work done on the object is independent of the path traversed by the object. It depends only on the initial and final positions of the object. Let me summarize what we have been talking about. To describe work done on an object, we require the magnitude of the net force acting on the object, its initial position, and its final position. We do not require the direction of motion of the object. Thus, work is a scalar quantity. Now, I'd like you to consider two cases. In the first case, a force of 100 Newton displaces a block A on a smooth floor through 5 meters by pushing it horizontally. And in the second case, a force of 25 Newton displaces a block B on a smooth floor through 20 meters by pulling it horizontally. Can you tell me in which case more work has been done?
Let me see. Even though the force applied and the displacement of the blocks in both the cases is different, the product of the force applied on the blocks and their displacement seems to be the same. Work done on the block A is the product of 100 Newton and 5 meters, which is equal to 500 joule. Work done on block B is equal to 25 Newton multiplied by 20 meters, which is equal to 500 joule. That means that the work done in both these cases is the same.
Correct. Very good. Now we have learned to examine situations to determine whether or not work is done in a specific situation. However, the interesting thing about work is that it can be positive as well as negative.
Really? How is that?
Let me explain through some examples. First, consider two situations where force and displacement are in the same direction. Case 1. A boy shifts a table from one spot to another in a room. He does this by pushing it over the smooth floor of the room. Case 2. A small child pulls a toy cart with rubber wheels over a smooth floor. In both the cases, some work is done and the force and displacement are in the same direction. Where both the force and the displacement are in the same direction, the work done is called positive work.
What about negative work?
I'm coming to that. Let us consider two more cases. Case 1. A porter pushes a wooden block on a rough surface. Here, the porter applies force on the block in the forward direction. This force does positive work since the direction of the applied force is the same as that of the displacement of the block. However, the frictional force on the block does negative work since the direction of the frictional force on the block is opposite to that of the displacement of the block. Case 2. A stout person is walking. A lean man tries to stop him. The stout man overcomes the force applied by the lean man and continues to walk, but he is walking slower than before. Here, the direction of the force applied on the stout person is opposite that of his displacement. Thus, the work done on the stout person by the lean person is negative. So we can say that when the force acts in a direction opposite to the direction of displacement, the work done is negative. In such situations, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is the product of F and minus S, or the product of minus F and S.
Okay, I think I got it.
This brings us to the end of this lesson on work. In this lesson, you learned what work means in terms of signs. You also learned to distinguish between positive and negative work, as well as calculate work done. The section Unsolved Problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.